I want to do one more of those questions from the previous section. And it's find the volume between these two surfaces. So if you do the first surface, it looks something like this. And if you do the second surface, it looks something like this. And when they interact, you get a thing that kind of looks like an acorn. You trust me on that? So we're being asked to find the volume of this acorn. That one there, this one here, is basically that surface here, right? The top one. And this one here is the bottom. Now we want to set this up as a volume question. So when you do a volume question, isn't it going to be 1? Right? The function is just 1. And so all we need to do is find the limits of integration. And when it's a volume question, the most common one is Z. And so the two Z guys that I'm going to use are these guys here. So they're going to be 15 take away x squared, take away y squared. And this guy's going to be 6 plus x squared plus y squared. Are you comfortable? Top guy, take away bottom guy, right? Z to Z. Now, it might be the next time that is Z equals x add y, and this is Z equals, 5x minus y, whatever it is, top take away bottom. So if you see two equations with Z's in them, there's a great chance that that is going to be your two limits of integration. So far, so good. Now, what does the bottom look like? Well, last time I kept on saying, and I shouldn't have, that it was the ground, because it is the ground, but it's the shadow of the intersection. So can you imagine they intersect here and you project that onto the ground? So how do we find what that looks like? Well, you set each equation equal to each other. And then if you add and subtract, you get that. And if you divide by 2, you get that. Don't we basically know what the ground looks like now? Isn't it a circle, which is pretty obvious? And isn't the square root of that is 3 over root 2. So that guy there, oops, is 3 over root 2. So I can now do, I wish I gave myself a little bit more room, but can't I do theta equals 0 to theta equals 2 pi, because it's the whole circle? And then can't I do r equals 0 to r equals 3 over root 2? Now we've set up a really ugly triple integral, but would you agree it's also quite doable? Right, you should be able to do it. Does that question help you a little bit when you're looking at the x, y, and z's? Does that idea kind of make it a little bit coherent? Try and do z's first and then see what you get after that. In this case, we're specializing only on questions that involve volumes. Of course, if that question had a function here, wouldn't I just replace the 1 by whatever f of x, y was, right? So we could still do it. So we're now moving on to our last section for the midterm. And it's, I'll put my heading down. Section 15.7. And we are going to still be doing triple integrals, but we're going to use what are called cylindrical coordinates. It's very, very similar to polar in 2D, right? So you remember you do double integrals using polar coordinate system. Cylindrical coordinate system is very similar. So let's just do a quick reminder of what polar looks like. If you want to tell someone a point in 2D space, you can do it by giving the distance r and the angle theta. And wasn't the rule that you should use polar coordinates if there's some kind of circle or a piece of a circle involved in the region that you're integrating over, right? Right, in the 3D system, and God, this is going to be painful. I can tell you right now, it's not hard, it's just I can't draw well. If you want to tell someone a point in 3-dimensional space, and you want to use what is called cylindrical coordinates, what you have to do here is drop this down with an invisible dotted line until you hit the floor. And I don't know why that's said, right? To get a guy called Q. You then use polar coordinates to describe this guy, and the Z coordinate is the same. So can you imagine you start on the ground and you go 30 degrees, 5 away from the origin, 50 feet up. So do you notice the Z still Z? So when you do something in polar coordinates, it's typically R, theta, Z. Does that make sense that you can tell me where something in 3D is by using R, theta, and its height Z? Right, so you imagine rotating that. I think it's got a good name. Can you imagine that if you rotate this angle and then you move the height up and down, don't you basically make a cylinder? Right, like a pipe. You can orientate cylindrical coordinates so that the cylinder goes in the x-axis or the y-axis. And if you do that, you just say x r theta, r y theta, right? You can switch them around. That's pretty uncommon, but I mean, it could happen. This is pretty much the standard way that we would do things. And why is that helpful? Well, we've actually done cylindrical coordinates before. In fact, if I see that question I just did a minute ago, didn't we turn the base into r's and thetas because it was easy to do? That was an example of using cylindrical coordinates. So, to remind you, x gets replaced by r cos theta. Y gets replaced by r sin theta. Z, I don't know if you'd say it gets replaced by Z, but it stays as Z. And you know the classic dV guy? He gets replaced by r, dr, d theta, dz. Where on earth did this little baby r come from? Wasn't it in the 2D integrals? So it don't matter. You could, do you know you could theoretically, couldn't you do 4th dimensional, right? X, Y, Z, W. And couldn't you make X and Y use polar and Z and W's just stay as Z's and W's? Couldn't you create a 4th dimensional equivalent to cylindrical coordinates? So far, so good. So let's do some practice. Straight in with question 1. Let's do some practice of taking a surface, a 3-dimensional surface, and trying to write it down in terms of Z equals a function of r and theta, right? Try and write it down of what it might look like in polar format, right? So if I went and said to you, x squared plus y squared plus z squared equals 9. Just curious, doesn't matter for the question. Do you know what that surface is? You got a gut feeling what it might be?
Is it a sphere?
It is, it's the surface of a sphere. Does that kind of make sense? It probably would be, and it is. Now, what do these two guys get you? In polar form, what does x squared plus y squared become?
R squared.
And so couldn't I just say that? Technically speaking, shouldn't I probably do that? But can you see in some cases, isn't it better just leaving the thing as z squared? Just looks pretty. So how about z equals 8x squared take away 8y squared. Now x is r cos theta squared, y is r sin theta squared. If I multiply this out, I get 8r squared cos squared theta. If I multiply this out, I get 8r squared sin squared theta. And we're always on the lookout for style points, because style points are going to make the integration easier as well. I need some help here. Anything you could do here to make this prettier?
We go on 8r squared.
Great. And that would leave me with a cos squared theta, take a sin squared theta. That's a good thing to do. What you might not know, and hopefully you do, is that this is a trig identity. Who is cos squared take away sin squared when it's at home?
Cos square or cos 2 theta.
You nailed it. There you go. Now, can you imagine you're doing a triple integral and it's one of those z equals this and z equals that? Wouldn't you want to turn them into r's and thetas in both cases so that you could do your z equals r to z equals r and then do the thetas and the r's that come after that? So this is a good skill set to be able to work with. Here is actually a plane in 3D. So I'm going to find out what z is in terms of r and theta. This one is not going to be very pretty, but still doable. X is going to be 3r cos theta, and y is going to be r sin theta. And really there's nothing I can do, so the question's finished. Are you comfortable about converting x, y, z equations into a z equals or maybe a z squared equals in some cases? You feel comfortable about the algebra? Every x turns into r cos theta, every y turns into r sin theta, and then you try and make it as pretty as you can after that. Any questions? Okay. Let me show you an application of that. Okay, we got one. Why has it got the answers? Go away. Thought I'd killed him. That's fair. Okay. This guy is question 3. You just won't be able to see the 3 because when I move it up, it goes too big, and when I move it down, it's too small. Here is our shape. I might be able to make it a little bit bigger, actually. Yeah, okay. We have essentially, well, can you imagine? To me, it looks like a bullet, and then they've cut it in half. Do you see the shape is only the right-hand side piece, right? This surface here is z equals 2 take away x squared take away y squared. And the surface finishes on the bottom, right, which is here. The function that we're going to integrate is this guy. So that function belongs here. So that's going to be 7. And right now I'm going to call it x squared plus y squared, but it's not going to stay that way forever. Right. So let's look at what the limits of integration would be. This curved surface has this equation. So starts off at 0, oh, they tell me that, and it finishes off, well, if you go vertically upwards, won't you hit this dome? And that would be to z equals 2 take away x squared, take away y squared. So far, so good, right? Now, the way these are written right now are all in terms of x's and y's, and I'm going to come back to them. But these two guys are going to be in terms of r and theta. And, well, actually, they've missed an r there, but we'll worry about that in a minute. If you look at this region here, I'm going to have to redraw it orientation on a piece of paper. And let's set up what the floor looks like in terms of r and theta, right? So we've got half a circle, and the half of the circle goes this way. Yes, it does. Good. So that's what the floor, it kind of looks like that in the picture, but that was orientation. Now, what do I know about this circle? Well, they told me that it's part of a cylinder that looks like this, and they told me that the equation of this cylinder is x squared plus y squared equals 1, which is just basically telling me that I have a circle of radius 1. But what will be the range of theta to generate this half circle?
Zero to pi.
Agreed. Okay, so those guys I'm now going to return and stick them back inside our integration guy. So theta goes at the end, so that's going to be theta to pi, and r goes from 0 to 1, and that goes 1. And what do you think I'm going to do about all this stuff? Well, you can't have x's and y's when you do cylindrical coordinates. You must have r's and thetas, right? So everything is going to be in terms of r and theta. So see this guy here? Minus x squared minus y squared. What does that look like when you convert it into polar?
Negative r squared.
Okay. Of course, you don't do z equals even if I do. You do that. What's this guy going to become?
Would it be 7r cubed since they left out the r?
Well, it's going to be 7r squared, and then I'm going to put out the r that they wanted, and then I'm going to say, well, that really just becomes r cubed eventually. Would you agree? And then you integrate in the usual triple product way, right? So it'll almost certainly just be various versions of power rule. Darn it, I was hoping I could do a check on it, but I can do a check up here because I switched it off. Key, and go for it. Isn't that what I had written before they rubbed it out? So we know I got it right. And this particular integral is going to be that. So we are really just using cylindrical coordinate system to make triple integrals that involve pieces of circles, right? So if there's a circle involved somewhere, you're probably going to have to do cylindrical coordinates. Now, they ask you in a lot of questions to sketch something. Good luck sketching half of these shapes. So I'm not even going to try. They don't ask you to actually do it. So this is going to be z equals to z equals. And this is going to be theta equals to theta equals. And this is going to be r equals to r equals. And they've got an r, a dz, a d theta, and finally a dr. Now, since this contains an r, these are not separable. So I'm going to do this integral first. So it's going to be from 0 to 7 and from 0 to 2 pi. If you integrate r with respect to z, what do you get? Integrate r with respect to z.
You get ZR.
Okay. And evaluated from 0 to r. And you get r squared take away none. So you just basically get r squared d theta dr. Is this separable? Numbers? Check. Break this part? Check. So I'm going to do from 0 to 7 of r squared and from 0 to 2 pi of 1. And isn't that basically 2 pi? And this is 1/3 r cubed using the power rule for integration. And whatever 7 cubed is divided by 3. 343 thirds, take away nothing, times 2 pi, 686 thirds with a pi, and it's right, so that's good. So it's not a big leap, isn't it? Isn't it kind of sort of what you've been doing anyway? You're just noticing now that they're formalizing the fact that if a shape has circles in it, that you would probably want to do cylindrical, which is essentially polar as well, isn't it? Because it finishes that way. If they give you an integral, then I guess you don't have anything to worry about. So let's look at question 5, where we're being asked to find this triple integral. And the guy we're going to do it to is x squared plus y squared. And E, which is this region, lies inside the cylinder, that guy, and between z equals -2 and z equals 1. So can you imagine a cylinder? The xy plane would probably be in this region, and the cylinder, some of it's below the floor and some of it's above the floor. And the heights they're talking about is that would be at a height of z equals 1, right? The level. And this would be at the height of z equals -2. So that's the region E. Well, I can tell you right now, isn't that the important part? So I'm going to do the integral from theta equals 0 to theta equals 2 pi. And from r equals, what's that, 16? So that's going to be 0 to r equals 4. And z is going to be from -2 to z equals 2. This guy here is going to get turned into polar, isn't it? So what is the simplest version of x squared plus y squared inside the square root?
We'll have an R squared and then R on the outside since we're converting to polar.
Okay, so square root of r squared is r, and then another r gets you back to r squared. I agree. And then when you do a dz, a dr, and finally a d theta. Is this integral, this triple integral, is this separable? Everybody is a number? Check. Is this separable? I can't think of a better word, right? Yes. So if you wanted to do this one, it would be theta equals 0 to 2 pi of 1. R equals 0 to r equals 4 of r squared. And z equals -2 to z equals, I've said -2 to 2, that's a 1 actually. Z equals 2 to 1 of 1 dz. Okay, that guy I can do in my head is 2 pi. This guy I can do in my head is 3. And this guy is a third r cubed from 0 to 4. And that's 64 thirds times 2, 128 thirds times another 3. Oh, that cancels out that guy. I make it 128 pi. And I am right, it's 128 pi. So I cut a lot of corners there, but you can check it. Okay, for the next one, I'm only going to set up the limits of integration because once that's done, I think the question becomes pretty straightforward. So in this one, we're being asked to find the triple integral of z. And the region E is described as a parabola. And a plane. I'm doing the first one because he's easy. Well, sort of easy. I'm not 100% sure unless I put it into Weber sign. Not Weber sign, unless I put it into GeoBra. I don't know which one of these is bigger. Right, is 16 up here and the curve's down there, is curve up here and 16's here, right? Is it above it? Is it below it? So you know whatever one I pick is going to be the wrong one. So I'm going to pick the origin, 0, 0. And at 0, 0, won't z be 0 and won't z be 16? Right? When x is 0 and y is 0, won't this value be 0 and this one be 16? So that has told me that you are the small guy and you are the big guy. Do you see how I cheated? Just pick x is 0, y is 0, right? And figure out which one's above and which one's below. Now, the next two guys are going to be the polar. And z is okay right now. What am I going to turn this fella into? Because remember, we don't have x's and y's. We must have polar. What will z equals x squared plus y squared turn into in polar format?
R squared.
Now, you remember that acorn one where I had a guy above and a guy below, and I said it's not necessarily the floor, but it's the intersection of them projected on the floor. And the way that we do that is we say that these are equal to each other. Now, when you make them equal to each other, can you see the shadow it makes on the floor? It's a circle, right? And so I know right away that theta is a whole circle and the radius of this is 4. Are you comfortable about how we constructed the integral? Are we good? Now, couldn't this have been 16 take away an x squared, take away a y squared, right? Be a bit uglier, but it could have been. And if it had been, wouldn't I make them equal and find out what the intersection of the two shapes was, and then that would be the shadow on the floor, right? It would still be, you know, x squared plus y squared equals 8 or something, but it would be a shadow floating above the floor. And that's the end of that question. Are we good? Again, setting up is the fun part. In this case, we're doing a triple integral over E. The function is not very pretty, at least for turning into cylindrical coordinate system. And the region E, it's in the first octant. Isn't that x, y, and 0? X, y, and z. Isn't the first octant where everybody is positive, right? Remember the first 1/8 of the 3D space. And z equals x squared plus y squared. And, oh, I changed that. I scanned to the wrong one. And it's underneath this fella. Okay. Technically, greater than or equal to. Ooh, we have an issue here. Let's do the z parts first. Since it's in the first octant, won't z be 0? Right, that's the floor. And then it goes up to 16, take away this. But if you convert this into polar, we get that guy. Are we comfortable with that? Right. Now, we have to figure out, what does that look like as a shadow on this world? Well, in this particular case, isn't this actually is going to be the floor? Isn't z going to be 0? And so what we're looking at is 0 equals, sorry about that, equals that. And so, and you are immediately, if you were me, going to jump into the wrong conclusion. Oh yeah, theta is 0 to 2 pi, r is going to be 0 to 4. But I forgot to take into account that you're in the first octant. And when you're in the first octant, doesn't that mean you're only this piece of the circle on the floor? Agreed? So that is going to change some of my answer. Isn't r going to go from 0 to 4? And theta, what is the range of theta in this question?
Zero to pi halves.
Agreed. And to finish with, x and y have to be turned into the polar form. So x is r cos theta, y is r sin theta. And isn't z okay to be called z? And the dv, because I don't have enough room, is going to be r dz dr d theta. And I am really glad that I'm stopping here. That is going to be one ugly triple integral, isn't it? It's not that it's going to be that, it's just going to be massively big. It's not difficult, it's just massively big. And I'm glad I can say ... So, question 9. Find the volume. When they say find the volume, doesn't that mean we're doing that? They don't mention that. They just say find the volume. But I know that's the triple integral, right? And we are looking at find the volume of the solid that lies within the cylinder. So that's x squared plus y squared equals 16. And a sphere, which is x squared plus y squared plus z squared equals 49. I'm going to have to try and draw this. So no laughing unless you can draw better. We have a sphere of radius 7. Yep, that doesn't even vaguely look like a sphere. Can you pretend that is a sphere, radius 7? Inside that sphere, there is a cylinder called x squared plus y squared equals 4. It's a little guy that looks like this, right? And it goes all the way up forever, and it goes all the way down forever. And it looks something like this. When you look at what the solid that they're asking us to find the value of, can you imagine that this cylinder is actually a drill hole? So what you've got is a sphere and somebody drill a hole right through it, right? And we're trying to find the volume of that tube. Can you visualize it? I think that's actually a little bit better than that picture, but you can imagine that's a hard question to answer. Now you might think, oh no, it's not. I know how you get the volume of a, a sphere. It's not that hard. It's 4/3 pi r cubed. Boom, I'm done. I know how you get a cylinder, right? Isn't it just pi r squared h? Shouldn't I just take one answer away from the other? Well, you're forgetting a little bit. When the hole finally pops up there, doesn't it kill a little bit of a curved part of the sphere? Isn't that gone? And at the bottom, doesn't it kill it? So it's not as simple as just finding those two guys, but we do have to figure out, right, what the limits of integration are. Okay. And since I've made so much of a mess here, you don't need to do this. I'll just reset it over here. We need to figure out what Z is going to be. Agreed? The limits of integration of Z. Any ideas? Just using these two guys, how you might be able to put a range of values on Z.
Square root of 49 minus r squared. Plus or minus.
Yes. Yeah, you are bang on it. Not the way I would written it, but that's not a problem. You've nailed it. You want to explain the other 4 lines between the answer you just gave and what's in front of us.
Well, first converting the x squared plus y squared into the r squared, and then subtracting that from both sides for the x squared plus y squared plus z squared equals 49, and then taking the square root of both sides.
Okay, so if you took this guy, if I can.
Yes.
Is that essentially what you did?
Yep.
Okay, now, looks good. So what would that look like? Well, I'm pretty sure negative goes first. This is one of the few times where I don't need to worry about who is first and who is second. That's a good start. We know it's going to be 1, don't we? And we know it's going to be r dz because of the way I've set it up. I guess all we need to do now is figure out what the intersection looks like. Well, we kind of know. Isn't it going to be a circle? And isn't the circle basically that guy? And the radius is what, 4? So far, so good. So how about theta equals 0 to theta equals 2 pi, r equals 0 to r equals 4. And that bit there, I don't need to worry about. Actually, if somebody says to you r squared equals 16, is it not r equals 4? And is it not a circle, radius 4? And it's the same information. Now we would do dr and dz. I think I should take this one step closer. Okay, so theta is still going to be 0 to 2 pi, and r is still going to be from 0 to 4. And I'm going to integrate r with respect to z, which just gets you rz. And it's going to be evaluated at negative the square root of 49 take away r squared, and positive the square root of 49 take away r squared. Right. And then we'll do the dr and the d theta after that. Okay. If you replace r with this guy, take away r with that guy, you actually get the same thing twice. You get r times this guy plus another r times that guy. And can you trust me that this is what you end up with? Right, you get this guy, take away a negative means you can add it. And we're going to do from 0 to 4 and from 0 to 2 pi. And the reason I wanted to do this is so I can bug Mia. You want to get us out of a bit of a hole here, Mia? What technique will we use to integrate this fella here?
U sub.
U sub. I think I've picked in poor Mia too many times now. You've done all the homework, not Mia. You as a class have done a lot of questions. Were there many integration by parts situations, or was it just power rules and U subs? Did any integration by parts actually happen? I'm just curious. Can anybody recollect any integration by parts?
There was at least one.
Right.
I can't remember what it was though.
So would it be fair in saying, when in doubt, look for a U sub? At least in the context of the amount of times it has happened compared to anything else. And I would ... after that. Any questions so far? Right, why don't we spend the last few minutes reminding you about your midterm? I've done this speech a few times, but with the exception of maybe one of you, you haven't quite heard it maybe often enough yet. Let's talk about your midterm. So while I'm doing that, why don't you put your last name down for attendance? Put this on student view. No, let's leave student view, make sure I'm in the right one, unless you want to find out what my intro to stats class is going to be doing. Right, here's ours. Now we'll put it in student view. Okay. For us, it's going to be from 12 to 2. No one's contacted me, well, with one exception, about that being an issue. Hopefully it isn't. Right. So it's going to be 2. It's going to take place, let's make this a bit easy to see here. It's going to take place in Canvas. So it's going to be a PDF. The topics that we are going to be covering are all of these. As you can see, triple integrals, which with a bit of luck will finish tomorrow. And that means we can spend Friday just revising for the midterm, right? So you bring questions and we'll go over stuff. Your test will be chronological order. So the first question will be partial derivatives. And the last question you will see is triple integrals. And I think, yeah, I don't think I'm giving too much away. You are guaranteed one question at least from every single one of these sections. And for most of them, only one question. Right? There's only so much you can do in 2 hours. Right? Not all questions will be worth the same. Would you agree that when you have to find the center of mass, there's a lot more work than if you have to do a simple triple integral, right? So depending on the work, some questions are going to be worth more or less than the other. And it's going to be out of 200. You're not allowed to cheat, but you can use any notes you like, as long as they're physically written down. And I am not testing your ability to be able to look up other people's questions. If you had to write down everything, you're never going to finish the test in time, because you're going to be looking through lots of pages just to find the question that looks just like this one, to read over how it's done, and then to try and duplicate it with different equation and different numbers, right? So that's probably not a good usage of your time. I think it's much better to have your major notes being quite small. Put all the really important stuff. So if you can't remember what the integral of secant is, right, you might put that down, because you keep saying, nah, can't remember it, I'll write it down. Now, Sunday, midnight, drop dead date for all assignments. No extensions, nothing. So if you can't do it by Sunday, you've lost the points. And I've told this to everyone, so I'll tell you why. I'm forcing you to be prepared for your online. for your test. You have to be, so if we gave extensions, how can you do the midterm if you haven't done the homework for it, right? It's just not going to work. So we're forcing you. So you don't have a lot of work. You know, you kind of signed up for it, right? So it's not a surprise. That's what happens. Probably done this before. There is the Zoom link. We don't use our class link. We have a special link. The midterm exam will appear here. When you are finished, you're going to show me you're working, and you're going to use the software like Microsoft Lens. So click on upload your working, do all the stuff we told you about last time, practice on it. If you don't want to use Microsoft Lens, use whatever software you've been using in your English class to do the same job. If you've got a printer that scans, use that. The only two guys are going to have is GeoBra, which you might want to use occasionally. Do you know that one that I was trying to do the Acorn for? You could maybe use it for that. I'm not sure. Yeah, you might use Desmos if you're trying to see what something looked like in Bowler, I guess. And there's just a practice. Kind of see the question. Now, there is a good example of that Acorn question. Much better if you use someone else's, right? And can you see the circle, which is its shadow on the floor that I was talking about? That's visually what it looks like. And here are the solutions. So you can do what you wish with that. You can choose to use it or not. When the midterm happens, everything in WebAssign will disappear. And everything in Canvas, except this module here, will disappear. And that will disappear as well for obvious reasons. All right, any last minute questions? Anything you need me to talk about?
Isn't the book on WebAssign?
Yes.
Okay.
If you
And,
have to look
that's-
up the book, then look up the section, then read 5 minutes how to do it, and then convert it.
No, it was
You're
for
running.
the doesn't it have a bunch of integrals at the back?
Oh, that's okay, yeah. You would certainly use it for standard integrals. The
Yeah.
book's not going to disappear. The book's always going to be there. But you
Oh,
could
got it.
couldn't you simply just get a textbook and use that, right? Or you could just write the whole tour. There is nothing wrong in you doing that if you want to, especially if it was a standard integral. To be honest with you, if it was a standard integral, in the question, I would say, hint, the integral to secant theta tan theta is, and I'd write the horrible answer down. If I ever did a question like that, that is not a suggestion. That is, please make sure that you've got the integral of secant tan when you're finished, right? Because if you don't get that, something went wrong, right? So I
Yeah,
would
that makes
probably do
sense.
it. I would probably do it that way rather than have you, you know, hunting through a textbook where you're not quite sure where to put the answer. But that won't happen a lot. But I do expect you to know all the standard integrals, right? So if I say to you the integral of secant squared, I expect you to know what that one is. Anybody going to volunteer the answer? What's the integral of secant squared?
Should be tangent, right?
It is. And what's the integral of secant tan? Because that's actually is a standard one.
Isn't that secant?
Yeah.
Yeah.
Now, if you're a bit rusty in those you better write that, right? Because if you have to go hunting for it, you'll be losing valuable time. Are we good? So if somebody comes up on Monday and says, what midterm? Maggie, I'm allowed to throw things at them. Mia, I'm allowed to swear at them. And Eric, I'm allowed to fail them, right?
Yep.
Okay. So it won't be any of you lot who will try that one. Okay, bye-bye, guys. Have a nice time. See you tomorrow. I'll hang about for any questions.
Actually, I do got a question. but
Yes,
it's,
sure.
I'm a little ahead on the homework. One-
Nothing wrong with that.
no, okay, so number 12,
On what section, sorry?
15.7, the one we were just on.
Whoa, you are well ahead. Good man. Let me find it for you.
Yeah.
We may not have covered that yet, in which case I'll probably say, do you want to wait until then? And we can do it then. So anyway, what question was it again?
It's number 12. I'll wait if.
It might not be. I haven't looked at it yet. I just want to see it.
That one just keeps throwing me
Oh,
off.
guys. Right. So you've got a Z equals. Right, let me write down. Let me. Where am I? I don't know where I am. I'm here. Okay. So you have got a Z equals this fella. And you've got a sphere, which is, in your question, it's that guy. Is that right? And you're being asked to find a volume. So I already know what my triple integral in a very basic format is going to be that guy. Great.
Yes.
And I all kind of know that I'm going to have R and theta here, right? But I definitely know I'm going to start with the Z's. And then it's going to be 1 times R. So it's going to be R,
Yep.
dz, probably dr d theta, right?
Yes.
Now, when I look at these two guys are going to be my Z's, right? Here and here. And I'm going to have to turn them into, eventually, I'm going to have to turn them into R's and thetas, right? But right now, I'm just going to match them up as they are. Well, one of these two guys is going to be in the bottom. If I do 0, 0, 0, 0 makes that nothing. 0, 0 makes that a number. Okay, so I know who the big guy is going to be. It's going to be this one. This one I know, right? He's a small one. Oh, wait a minute. Shouldn't I just call him R? Square it, right. Now, this fella's a bit messier, but if I rearrange him, he's 162, take away x squared, take away y squared. So far, so good?
Yep.
And if I assume that he's positive, because he's bigger than this guy, and this guy's positive, then I only need to do that guy.
Yes.
So I should plan ahead, drop that an inch, but too late now. We want to do our R values and our theta values, right?
Yes.
So we need to find out what happens when this guy meets that guy. And they're probably going to meet above the XY plane. So I have to find out what they look like when they intersect and then drop the damn thing down to the ground, right? So what I do is I'm going to make these equal. So it's going to be x squared plus y squared. But instead of z squared, add that guy squared. And it's equal to 162.
Yes.
And that's going to be x squared plus y squared plus another x squared plus another y squared is 162. And that's going to be x squared plus y squared equals 81. And I can see a circle, radius 9. No indication that it's not a whole circle. From 0 to 2 pi and from 0 to 9. Does that make sense?
Yes.
And yes, you are going to end up with a u sub. And it's going to be u equals 162 minus r squared, but that's going to happen later, right? Because when you integrate that, aren't you going to get rz again?
Yes.
And this particular case, you're going to have an r ugly square root, take away, I think it's going to be take away an r squared.
It should be an R squared. Yes.
Yeah, so, yeah, that's fine. One's a u sub and the other's just a power rule. And then well, actually, you've got numbers, so it's not so bad after that. 0 to 9 and then 0 to 2 pi for the theta. That makes sense.
Maybe I'm doing the use of, bro.
I don't know. If you put the thing in, it's going to be theta equals 0 to theta equals 2 pi.
Yeah.
And it's going to be r equals 0 to r equals 9. This guy becomes ZR, evaluated at z equals r on one side and z equals square root of 162 take away r squared on the other side. And then you'll do the dr d theta after that. So it's from here to here, and then from here to here. What we got here, we're going to have r square root of 162 take away r squared minus an r squared dr d theta. I would take care of these as two separate integrals just so that they don't interfere with you. So can you imagine a 0 to 2 pi, 0 to 9, the ugly one? Take away 0 to 2 pi, 0 to 9 r squared. And that one will get you some, and this is the guy I'm talking about with the U sub. So the U sub you're going to use is this fella. If you differentiate with respect to r, you get that. If you do the crossover, you get that. Okay, and then you divide to isolate the dr. So this integral here will be from 0 to 2 pi, and then it's going to be r square root of u times -1 over 2r du.
Yeah, I left the R out of that. That's
Okay.
right.
Okay.
I
So
see it.
yeah, these are cancelling. You probably would want to rewrite the square root as a half power. So it's -1/2 u to the half power.
Yep.
But that, you know, it comes out in some ridiculous. I can't see this being pressed, so it's going to be some really ugly looking answer.
Yeah, I just assumed I forgot to add the R next to the square root. 162 R squared. No, whatever.
Wait.
Thank you.
You're welcome. Okay, any questions? Anyone else?
Yeah, I had a question about more like conceptually, whenever you're
Sure.
doing the triple integral of one, that's like the area of a 3D like space, correct?
It's the volume of the 3D
Oh
space.
yeah, the volume I meant. And then but for the double like integral over a rectangle, is that also the volume of that space? Or
If it's
is
a double integral of one, it's the area of the 2D space. So
okay.
a double integral of 1 dA gives you the area of the region D, right? And if you have a triple integral over 1, that will generate the volume of the 3D region E. Technically, if you want to hurt your brain, the R, not even sure what you'd call this thing, W. Wouldn't that represent the volume, if you want to call it volume, of a fourth dimensional object? It kind of loses reality after 3, right? But
Okay, that makes sense.
yeah, a lot of weird math gets done beyond 3 dimensions. So it isn't inconceivable that there might be some people in the, you know, the theoretical physics world who do quadruple integrals. Right?
Okay, so then if you take a double integral of like a function or like a parabola or something, what is
Right.
that then?
What you're doing there is you're adding up the total of whatever this function is. So if someone went and said to you, I have a double integral of some region D, and it's x squared plus y squared, just for argument's sake, right? Then you've got a region in 2D space, which is, let's say it's that trapezium. On this trapezium, at any given value of x and y, this is what it's equal to. So imagine this represents perhaps the charge on a plate. So this double integral is summing up the total charge on that plane. So an integral is like adding things, right? Summing something up. And we're summing, if this represented what the charge would be at any given point, this is adding up the total charge. And if you think of every single point being a temperature, right, being energy, temperature, energy, whatever, aren't we adding up the total amount of temperature energy in that plane?
Okay, yeah, that makes a lot of sense. Thank you.
Right. It's quite good to do it when you do charge with positives and negatives, because you could have a plate whose total charge is 0, but it's made up of like a, you know, like a magnet. At one side it's positive and the other side it's negative. If they were equally charged, couldn't the total charge be 0? Even although at any given point there's a different amount of magnetism. Some are positive and the other would call, you know, north and south. You know, north is positive and south is negative.
That's interesting.
Well, if you can make a, I don't know how you can make it, because I don't think anyone's ever managed to do it yet, but see if you could make a shape have a positive charge to it. Oh, you could do that. Couldn't you take a plate and remove electrons in some way? Then wouldn't that plate have a net positive charge?
Makes sense to me.
Yeah, you could do that. So couldn't you have a plate with a negative, with a positive charge to it? And that plate would definitely have an affinity for grabbing electrons, because they don't like being positive. They don't like being anything charged, don't they? Try and balance. I wonder if that's how static things are. Do you know those air filters that suck dust out of the air? I wonder if they make themselves positively charged because particles and dust maybe are negatively charged. So it sucks them and grabs them.
I wonder.
I wonder.
Remember we did like a lot of charge and stuff in chemistry, but I haven't done chemistry in a while, so.
Yeah, and chemicals have charges, but the thing is, because they're together, the net effect is they have no charge. Although at one end it's plus and the you know, like an ion, right? At one side it's positive and negative, right?
Isn't it like in the magnets, like they're all pointing the same direction? That's why they're charged or something?
Yes, it is. If you can align them in a certain way, like iron is a very good element for aligning. You can make it positive at one side and negative at the other, which is essentially why it's a magnet.
Huh.
A lot of things you can't do that to, because I guess it's the shape of the molecule or the way the crystalline structure forms that they just don't allow you to do that. But I guess conceivably, it might be possible to take a ceramic and make it a magnet. In other words, have a ceramic magnet. I'm not sure how you would do it, but I mean, if we're pretty clever people, if there was a good reason to want to do that, somebody would figure out a way of making it happen.
Yeah, I
Even
wonder
if,
if
yeah,
a material, something like ceramic, which would be stronger than like the neodymium magnets or whatever.
right. I mean, there could be good reasons for doing it. For instance, ceramic can very often be a good heat conductor. So if you wanted a magnet to be able to tolerate high temperatures, wouldn't it be better to be ceramic than to be, you know, steel? Because steel will melt, right? And it'll get hot and all sorts of horrible things. Yeah, I guess you could take a ceramic and impregnate it with iron. Maybe that could be magnetized.
Or like if you rub like the magnet over a needle, it'll do the same thing. So maybe there's some way that you can do that with ceramic.
Yeah. See if any of these ideas make money. I want a cut. Right?
Alrighty, I'll
Because
let you.
you're young enough, Bernard, to actually do it, right? You magnet. If you come up with that and think, oh, I've got an idea, I'm going to do this. I want a cut.
You'll get some royalties.
Oh, I'll take some royalties. And I don't want 0.1% royalties. We're not going for that, right? I want a double digit in it, right? 99 would be good, but I'll settle for 10.
Very reasonable.
Very reasonable. Right. Okay. I'm out of here unless there's more questions.
I do have a question actually.
Yes. Mm-hmm.
So on the example of question number 9, where we had the cylinder going through the sphere,
Yes.
why was the limit of R 0 to 4?
When you looked at that cylinder and you did the shadow on it on the ground, it was a circle. And the cylinder was, I think, x squared plus y squared equals 16. Well, isn't that a radius 4 circle on the ground? So R was 0 to 4.
But what happened to the sphere?
The sphere is interacting with the cylinder, and the cylinder is the bit that's that we're well. You got me thinking here. If you look at it from vertically above, then this guy here is x squared plus y squared equals 16. And this is the sphere. What was the sphere again? It was
X squared plus y squared plus z squared is 49.
39?
49.
49.
So it would be
So
7.
this would be x squared plus y squared equals 49. So if it was this, I was assuming that it was the inside. But if it actually had been this region, wouldn't we have to do a between thing? Right, let's find that out. I'll go and see the answer to that one. What was that question again?
Number 9 from the last problem set.
Right. No, it's the inside one after all. So evidently they were looking at this guy. So when I went and said we were cutting a hole through a cylinder and we were finding the volume of what was left, it's actually the opposite of that. We're finding the volume of that bit, which is basically a cylinder with a little bit of a curved bit at the top and the bottom. So that was the volume that we were finding. Essentially the volume of the piece that you cut out of the shape, not the volume of what's left, but the piece that we cut out. Now, if it had been the volume that was left, which is what I said it was, it would be the donut. But actually it's the piece that you cut out, which would look something like this. Now, the reason it would have a little bump at the top and the other side, when it popped out, wouldn't it kill a little bit the sphere on both ends? And I'm just making it that. That is not, by the way, half a sphere, right? It's just a little bit of a curved part of a sphere, right? And it'd be very, very difficult to calculate it. And I think the phrasing might be it. The solid lies within both the cylinder and the sphere. Within means that. If they had said it was the volume inside the sphere but outside the cylinder, they'd be talking about that one.
Okay, wonderful, thank you. I was really confused.
I'm glad you thought about that, because if you think about it, that is just as likely until you realize what they were asking. And I said they were asking for this, which definitely didn't help when they were asking for this bag.
Okay, alrighty, thank you.
Okay.
Thank you.
You're welcome. Bye-bye, guys.